In the last three tutorials, we focused on building a system with a single agent. Starting from this tutorial, we want to build AI systems with several agents, where the agents of a system work together in order to achieve the goal of the system. In our platform, we allow you to build compound AI systems in the form of graphs of agents. Similar to the agents in our platform, the systems in our platform also support multitasking. What it means is that each system could have several tasks, where each task has its own designated graph of agents. We allow sharing agent nodes among the graphs of tasks of a given system. Sharing agent nodes among the system tasks results in saving resources while enhancing the performance of the systems. In the previous tutorial, we had the system with a single task, and that single task had a single agent doing image classification. Now our goal is to add a new task to this existing system where this new task has three agent nodes. We borrow and use the image classifier agent from the first task of the system as one of the nodes for this new task of the system. The other two agent nodes for this task of the system are a chatbot agent and a dataset agent. This is how we want to set up this multi-agent system. The dataset agent generates a MNIST handwritten image and passes it to the classifier agent. The classifier agent predicts the class of the input image and passes the predicted class to the chatbot node. The chatbot node is responsible to generate a MNIST-like 8x8 image for the predicted class. Here our goal is to show you how you could use our platform to build a compound AI system with agents with very different natures. In this example, our system consists of three agents with different natures. The first agent is the dataset agent that generates the data to be used by the other agents in our system. Another agent is the MNIST image classifier agent that relies on its internal data source and its internal deep learning model to learn how to do MNIST image classification. And the final agent is the chatbot agent that makes external API call in order to generate MNIST-like images. Here our goal is to show how the objective of an AI system could be realized by combining trainable agents with other common types of agents such as chatbots and data sources. The point is that when you think carefully about a compound AI system, it consists of several subtasks, and not for all of those subtasks, making LLM calls would be the most efficient and the best solution to get to their objectives. For a number of those subtasks, a better way and a more efficient way to implement them would be to use ML-based agents that could be trained by the AI systems internally. Essentially, that is the main message of this tutorial. For the image classification, we use a rather cheap ML model which is trained by the AI system internally instead of making external API calls for the image classification. In other words, we have a small ML-based agent that performs that task for us with cheaper price and better performance. Okay, let's start modifying our AI system. The first step is to create the chatbot agent. We name the chatbot agent OpenAI agent. First, I add a task named interactive to this chatbot agent. I will be using this task in order to experiment with this chatbot agent. In particular, I want this chatbot agent to behave like this. When I pass the predicted digit class to this chatbot agent, I want it to give me the MNES like 8 by 8 handwritten image corresponding to that digit. In order to enforce this behavior for this chatbot node, I have to come up with the appropriate system message for it. First, we add the chatbot node to the canvas. We name it chatbot. The chatbot node comes with different parameters that fully customize its behavior. Essentially, the chatbot node has two major operational modes. The first mode is API and the second mode is model. In the API mode, the chatbot makes external API calls in order to generate answers for the incoming inputs. Those external API calls are being configured by the API config parameter. In the model mode, the chatbot node creates a LLM internally in order to generate answers for the incoming inputs. The internal LLM is being configured by the autoregressive LLM config parameter. Here we choose API as the operational mode of the chatbot node, therefore we need to set the API config parameter. We set the model parameter to GPT 3.5 so that the chatbot node makes external API calls to this OpenAI model in order to generate answers. We set the timeout to 30 seconds so that the chatbot node waits at max 30 seconds to get the answers from OpenAI. For the authorization parameter, you have two options. Either to leave it blank, which in this case we will use our own OpenAI API key, or you could provide your own OpenAI API key. Another parameter of the chatbot node is the discourse parameter. If it is set to true, then the chatbot node will be executed in discourse mode, which means that the chat history is kept and is being sent to LLM in order to generate the next answer. If it is set to false, then the chatbot node will be executed in a single shot manner, and the chat history is not being sent to LLMs. The history size parameter is only relevant if the discourse parameter is set to true. If the history size is not set and the discourse mode is enabled, then the chat history is kept indefinitely. If the history size is set and the discourse mode is enabled, only the number of the latest conversation specified by the history size will be kept. Here we set the log chats parameter to true so that the chatbot conversations will be logged by the internal logger of the chatbot node. Next, we add an interactive input node to the canvas. We attach it to the chatbot node and we name it input. The interactive input node allows this task of the agent to be executed in an interactive manner, enabling the interactive behavior each time that this task of the agent wants to be executed. Its execution is being interrupted by the backend so that the user will provide the prompt corresponding to the interactive input node through the web app. Then the user input will be passed by the interactive input node to the chatbot node. Next, I will create a brand new system with the only purpose of experimenting with this chatbot agent. And this system is different from the system that I described before with the three agents. We name it OpenAI Sys. We added tasks to this system and we name it interactive. And we set the interactive parameter of this task to true so that this task will be executed in an interactive manner using the interactive input node of the chatbot agent. We add the OpenAI agent to the canvas. We switch to jobs in order to execute this system. We create a new job and we name it OpenAI job. We choose OpenAI Sys as the system of this job that will be executed. We add the session config to tell this job how to execute this system. We ask it to execute the interactive task of this system by setting the system task to interactive. Using agent tasks parameter, we tell the job object which tasks of the agents to execute. Given that the system task interactive has a single agent called OpenAI agent, we just need to add a single key value per to the agent tasks parameter. Here we are telling the agent to execute the interactive task of the agent OpenAI agent. We run the job. Given that this is an interactive job, we need to click on interactive button in order to interact with the chatbot agent. Using the input node DB drop-down menu, we could choose the interactive input node for which we want to provide the input. Given that this system task has a single interactive input node, this drop-down menu gives us a single option, which is that interactive input node. Now the platform provides us with the information regarding this interactive input node. Starting from the top, the system that this interactive input node belongs to is called OpenAI Sys. The system task associated with it is interactive. The agent that this interactive input node belongs to is OpenAI agent. The agent task associated with it is interactive, and the interactive node input name is input. We first need to click on Continue button in order to start providing the input for this interactive input. We first ask the chatbot node, "Who are you?" to see if the chatbot node actually works. Then we click on Submit button in order to submit the question to the chatbot node. In order to observe the response generated by the chatbot node, we choose the chatbot logger, which is the internal logger of the chatbot node. Here we see our question from the chatbot and also the answer generated by the chatbot. Our question is referred as user and the chatbot answer is referred as assistant. So far our chatbot is a general purpose chatbot, but we want to make it customized in a way that when we pass it the predicted digit class, it gives us the MNES like 8 by 8 image corresponding to that predicted class. In order to do so, we need to initialize the chatbot node with the appropriate system message. In general, the initialization of different nodes happen via the initconfigs parameter of the session parameter. Initconfig is a dictionary of the agent names to the dictionary of their configs. Here we have a single agent, which is the OpenAI agent. That is why the initconfigs parameter has a single key value pair, where key is set to OpenAI agent. The value 0 parameter refers to the initialization configs of the nodes of the OpenAI agent. As you remember, the OpenAI agent has two nodes. One node is the interactive input node, and the other node is the chatbot node. Here we just want to provide the initialization configuration for the chatbot node. That is why the value 0 dictionary has a single key value pair, where the key is set to chatbot and the value 0 refers to the chatbot initialization for the chatbot node. We choose the chatbot init config as the init config for the chatbot node. As part of the chatbot init config, we set the system message to an instruction that enforces the chatbot to output MNES-like 8x8 image when it receives an input digit. Later, we show you the exact instruction. We were able to find this instruction by a number of trial and error. We run the job. We submit the number 1 as the input for the chatbot. The chatbot returns an 8x8 array that looks like number 1. Perfect. It seems that we were able to find the correct configuration for the chatbot agent. Let's go back to our MNES agent and think about the changes that we need to make in this agent for it to work inside the compound AI system that we described earlier in this session. Currently, this agent has three tasks: train, viz, and test. The train task is used to train the deep learning model inside this agent using its internal dataset. The viz task visualizes the predictions made by the deep learning model. The test task is used to evaluate the predictions made by the internal model of this agent over the MNES test dataset. None of these tasks comes with an input node that allows the agent to receive inputs from the outside of the agent. That is what we need to do for this agent in order for it to work inside that compound AI system. Before making those changes, let's inspect the test task of this agent to remind us the nodes inside this agent. We add a new task called inference to this agent that will allow this agent to get inputs from the outside of the agent. Shareable nodes is the list of the nodes from the previous tasks of this agent that we could reuse them here. We add the MNES-CLSNet node, which has the image classification deep learning model. This node was originally defined inside the train task of this agent. Next, we add the softmax node. We attach the MNES-CLSNet node to the softmax node so that the logits generated by the MNES-CLSNet node will be converted into softmax distribution by the softmax node. We add the pick image node, which picks up the image tensor from its input dictionary, and we attach it to the MNES-CLSNet node. Next, we will add a logger node and we attach the softmax node to it so that we will be aware of the predicted softmax by the softmax node. We name it inference logger. We added dB fields corresponding to the incoming edge from the softmax node. We added dB field config to log the predicted softmax. We set the field type to number. Also, we set the outer index parameter and the inner index parameter to 0, since the predicted softmax by the softmax node will be wrapped inside two nested lists where each list has a single entry. Here, outer index refers to the index for the outer list, and the inner index refers to the index for the inner list. We do not need to set the index parameter and the key parameter, since the picked up object by the outer index and inner index will be the predicted softmax tensor and not a tuple or not a dictionary. As we mentioned before, the main reason behind this new task was to make this agent to be able to receive the inputs from the outside of the agent. Therefore, we need to have an input node for this task. The most straightforward way for this agent to receive inputs from the outside of the agent would be to change the mode of the pick image node from the internal node to an input node. Making the pick image node as the single input node for this task of the agent, when this agent is used inside the system, in that system, it could have only one incoming edge when this task of the agent is activated. In that case, the object delivered on that incoming edge will be passed to the pick image node. When we try to save the changes that we have made so far in this task, we get this error message from the system saying that the pick image cannot be an input node for this task because it has been an internal node for the train task. In other words, pick image being a shareable node, it could be either an internal node or an output node. Therefore, we make it back to an internal node. But we need to have an input node so that this task could receive inputs from the outside. For that purpose, we add a bypass node and we name it input. We attach it to the pick image node and we change its mode to input. Perfect, we are done with this new version of the MNES agent. Out of the three agents that we described at the beginning of this session, we have created the OpenAI agent and we have modified the MNES agent. The final agent is the dataset agent that we are going to create next. This agent will have a single task, and this task is responsible to pass MNES handwritten images to the MNES agent. This agent will have a single node, which is a dataset node. We set the built-in dataset parameter to MNES so that the dataset node relies on the platform internal MNES dataset to generate examples. We set the train parameter to false so that the test split of the MNIST dataset will be used. We add image and label keys to the keys parameter so that the output of the dataset node will be a dictionary with two keys, image and label, where the image key refers to the image tensor and the label key refers to the label tensor. We set the batch size to 1. We change the mode of this dataset node to output so that the generated dictionary by this dataset node will be used as the output of the agent. Great, we are done with the dataset agent. Now let's go back to the MNIST system and make it to use the newly created agents, the OpenAI agent and the dataset agent. Currently, the MNIST system has a single task, which is the MNIST task. The MNIST task has a single agent node, which is the MNIST agent. What we want to do is to remove this agent and add it again so that this system will have access to the new version of the MNIST agent that has the inference task. We add a new task for this system and we name it inference. This is the system task that we described at the beginning of this session with three agents, the dataset agent, the MNIST agent, and the OpenAI agent. We start building the inference task of the system. The Shareable Notes tab shows the agent notes from the previous tasks. The only existing task for this system is the MNIST task, which has a single agent node, which is the MNIST agent. That is why here we only see the MNIST agent. First, we add the MNIST agent. Next, we add the dataset agent from our agent personal library. We attach the dataset agent to the MNIST agent. Before adding the OpenAI agent, we want to make sure that this system task so far works as expected. In order to do so, we make a duplicate of the MNIST job and we name it infer job. As you remember from our agents tutorial, this job has three tasks: train, viz, and test. Out of these three tasks, we only want to keep the train task, since this is the task that would train the deep learning model inside the MNIST agent. We update the MNIST system of this job so that it gets access to the new version of the MNIST system. We add a new session config to the sessions parameter so that it executes the inference task of the MNIST system. That is why we set the system task parameter to inference. As part of the agent tasks parameter, we need to set the tasks for the agents that are part of the system task inference. The system task inference has two agents, the MNIST agent and dataset agent. Here we are telling the job object that we want to execute the inference task of the MNIST agent as part of this session. However, we forget to specify the task for the dataset agent. That is why we get an error message when we click on Run button. The error message is telling us that we need to specify the task for the dataset agent. We add the task for the dataset agent. We run the job. The job first executes the first session, which is the MNES task of the MNES system. The terrain loss logger and terrain eval logger are from the train task of the MNES agent. The inference logger is from the inference task of the MNES agent. Here we are able to see the logs for the predicted softmax, which shows that the inference task of the system actually works. However, our goal was not really to pass the predicted softmax distribution to the chatbot agent. Instead, we need to pass the predicted digit class to the chatbot agent. Therefore, we need to replace the softmax node of the inference task of the MNES agent by an argmax node. This argmax node receives the logits from the MNES CLSNet node and returns the index for the entry with the maximum logit. Okay, let's change the inference task of the MNES agent. First, we remove the softmax node. Next, we add a metagraph construct to create a customized argmax node. We name it argmax. We attach the MNES CLSNet node to it and attach this node to the logger node. Metagraph constructs allow us to create customized graphs of graph nodes. However, the metagraph that we want to create here is rather simple. It has a single graph node that acts as both input and output node for this metagraph. That single graph node itself has a single stage node that again acts as both input and output node for that graph node. Finally, that single stage node has a block with a single layer, which is the argmax layer. First, we add the single graph node as an input node for this metagraph. We choose graph config as its type. We name it argmax. Next, we add the single stage node as an input node for this graph node. We choose stage config as its type. We name it argmax. We set the block of this stage node to have a single layer, which is the argmax layer. We set the only output node for this graph construct to be the argmax stage node. We set the only output node for the metagraph construct to be the argmax graph node. We are done with the argmax node. Next, we attach the pick image node to the logger node so that the MNES images are being logged as well. We add a new DB fields for the second incoming edge from the pick image node. We add a DB field config to log the images. We set the field type to image. We set the outer index and inner index parameters to 0 because the tensor image output by the pick image node is wrapped inside two nested lists where each list has a single entry. Here, the outer index parameter refers to the index for the outer list, and the inner index parameter refers to the index for the inner list. We do not need to set the index parameter and the key parameter since the picked up object by the outer index and inner index parameters is not a tuple or a dictionary. We update the MNES system with the new version of the MNES agent that we just saved. We update the infer job by the new version of the MNES system. We run the job. This time the inference logger shows the predicted digit class as well as the input image. This is an output that we will be able to send to the chatbot agent.